Hello and welcome to another one video. What happens to an object after it enters a black hole? The first thing to understand is that it's not really a hole. It's a mass whose gravity is so strong that it literally absorbs all light. This means it's a planet-like sphere where light only goes in. It's like it's been covered with that new Vantablack paint. Once you get close, gravity will tear you apart, but the radiation will have cooked you alive long before that happens. Try to think of it like a planet with super density. Even all of the atoms have all of the extra space squished out of them. If the sun were a black hole, it'd only be 6 kilometers across, instead of the 1.4 million kilometers it is at the moment. If the sun was a 6 kilometers black hole, its gravity would be the same. The Earth would stay in orbit around it. A neutron star has a surface gravity that's about 10 to the 12 g, so a 1 with 12 zeros after it times Earth's gravity. A black hole has more, but the laws of physics sort of break when you get up to black hole numbers. That's to say 1 trillion g is weaker than a black hole's gravity. Once you hit the event horizon, gravity essentially becomes infinite. Let's just imagine that your ship is magic and can protect you until you land. You'd enter the space around the black hole, pass through the event horizon and descend towards the black hole. You wouldn't be able to see anything as all light would be pulled towards the black hole. You'd land and step from the ship. Instantly you'd be crushed to a layer thinner than paper. All of the atoms in your body would be crushed into a space smaller than that of a grain of salt. A black hole can be defined as an extreme curvature of space and time caused by mass leading to a singularity. All singularities are clothed with an event horizon. Neither light, nor information, nor gravity can reach us from beyond the event horizon. Nothing can ever come out. There is a great paradox about black holes, which is the result of applying relativistic formulas to the theory of a collapsing star. This is how all black holes start their existence. The theory of relativity shows that from a viewpoint within our universe, the star seems to freeze at its critical circumference of the event horizon and go no further. From the viewpoint of an observer on the surface of the star, or an infilling observer at some future time, however, the star would be crushed to a point in a short space of time. From Kip Thorne's book Black Holes and Time Warps. Einstein's outrageous legacy: like a rock dropped from a rooftop, the star's surface falls downward, shrinks inward, slowly at first, then more and more rapidly. Had Newton's laws of gravity been correct, this acceleration of the implosion would continue inexorably until the star, lacking any internal pressure, is crushed to a point at high speed. Not so according to Oppenheimer and Snyder's relativistic formulas. Instead, as the star nears its critical circumference, its shrinkage slows to a crawl. The smaller the star gets, the more slowly it implodes until it becomes frozen precisely at the critical circumference. No matter how long a time one waits, if one is at rest outside the star, that is, at rest in the static external reference frame, one will never be able to see the star implode through the critical circumference. That is the unequivocal message of Oppenheimer and Snyder's formulas. Is this freezing of the implosion caused by some unexpected general relativistic force inside the star? No, not at all, Oppenheimer and Snyder realized. Rather, it is caused by gravitational time dilation, the slowing of the flow of time, near the critical circumference. Time on the imploding star's surface, as seen by static external observers, must flow more and more slowly when the star approaches the critical circumference, and correspondingly everything occurring on or inside the star, including its implosion, must appear to go into slow motion and then gradually freeze. As peculiar as this might seem, even more peculiar was another prediction made by Oppenheimer and Snyder's formulas. Although, as seen by static external observers, the implosion freezes at the critical circumference, it does not freeze at all, as viewed by observers riding inward on the star's surface. If the star weighs a few solar masses and begins about the size of the sun, then as observed from its own surface, it implodes to the critical circumference in about an hour's time, and then keeps right on imploding past criticality and on into smaller circumferences. By looking at Oppenheimer and Snyder's formulas from the viewpoint of an observer on the star's surface, one can deduce the details of the implosion, even after the star sinks within its critical circumference. That is, one can discover that the star gets crunched to infinite density and zero volume, and one can deduce the details of the spacetime curvature at the crunch. P217 to 218. If you fall into a black hole, you will find you will be accelerated towards light speed. At the event horizon, that is precisely what you will become, but in the process you will also fast forward in a few minutes or hours to the end of the universe. Time dilation is the term for this. It affects our view of you falling in and your view of the universe as you fall in differently, but in a complementary way. What happens to your energy then? That's another question. But I don't believe energy can be created or destroyed. If I were to fall into a black hole, what would I experience? Is it true that if I fell into a black hole, I would go to another universe? What will happen to an atom if it fall into an black hole? There is a very interesting object just like black hole, called magnetar. It forms when a star is collapsing, but don't have enough to become a black hole. When an hydrogen atom comes into its close vicinity, the whole atom actually loses its fundamental property. Its electron gets ripped apart, whole atom's orbitals deforms into long cylindrical forms and complete incineration. This whole phenomenon happens because of astoundingly high magnetic fields. What we get from the above case that on such scales like black hole, center PF a star or even close to event horizon, the classical physics cease to act and modern physics like relativity, Hawking's radiation, quantum fluctuation, takes control of the whole outcomes. So, let's get going to case of you falling into a black hole, or event horizon to be precise. Case 1. Falling into a considerably small black hole, example a black hole formed by a star 10 times the size of our sun, average size. 1. Such black holes have quite smaller event horizon and can bend space-time much higher degrees, will not cause much observable time dilation. 2. It will be difficult to enter these kind of black holes without getting incinerated by chaotic accretion disk-formed revolving matter around the quite small circumference of the event horizon. 3. Let's assume that you are riding an indestructible spaceship directly toward black hole. Initially you would not feel any significance difference caused by space wrapping. But, just when you get close enough to event horizon, the gravitational pull by the black hole will start to increase exponentially, with the decreasing radial distance from the center of the black hole to the spaceship. For example, let's assume your spaceship is pointing directly toward the black hole, then the tip of the spaceship will feel higher gravitational attraction than the tail of your ship. This difference will increase super exponentially while you reach more closer to the event horizon. Your spaceship will start to elongate in length, just like the hydrogen atom in case of magnetar. No possible material could withstand such enormous force of elongation. Eventually you will disintegrate before reaching event horizon. 4. Let's say you somehow avoided disintegration before reaching event horizon, you would notice nothing. It will be extremely fast journey from event horizon to the singularity center of the black hole. You will see absolute darkness and absolute silence, as no relativistic motion of electromagnetic wave is possible in such gravitational field, and same for sound wave in case you are still in your unharmed spaceship. Tricky part. What happens at singularity is singularity have an ability to consume space-time itself. Some scientist believes that it opens portals to other dimensions or maybe other universe. It is theoretically possible to have an entire fucking universe within an infinite-size black hole. In such case you would enter into an entirely uncharted universe. This theory also defines a similar counterpart object in other dimension called while hole that throws matter and space-time consumed from this universe into other dimension or universe. But this is most unlikely to happen and is not that significant theory as it violates the second law of thermodynamics. This reduces the entropy of this universe. Much significant theory by Stephen Hawking suggests different aspect. He believes that black holes may have a well-defined surface under event horizon, and it would and should evaporate in finite amount of time radiation away all the matter in the form of X-rays. His theory is yet to be proven. In this scenario your spaceship will collapse into surface of black hole before reaching singularity and will evaporate from it in time in form of energy. Wait. How can anything escape from a black hole? It can and is called Hawking's radiation. It suggests that quantum fluctuations at event horizon can produce matter-antimatter pair in high quantity due to high energy fields caused by gravity. Most of such pairs recollapses to radiate energy, but at event horizon antimatter can fall into black hole to nullify matter in it, and matter part can be radiated from the surface of event horizon. Case 2. Falling into supermassive black hole. Example 40 million times massive black hole present at center of Milky Way. You will not feel any detectable change in gravitational attraction near event horizon because of our smaller size with respective to the black hole. Strange but true, we won't be able to detect event horizon before entering it. It's because of the size of the black hole. The accretion disk will not be that vigorously and relatively slow because of the great size of event horizon. We won't feel any change in gravitational fields due to much larger distance from the center. Unlike the case of smaller black hole where this change is super exponential. We will surely feel time dilation due to the huge mass of the black hole. You will age relatively slowly near this black hole with respective to the aging at Earth. You will feel time dilation if you return back from near the event horizon. In case you plans to return back to Earth after spending 1 year near event horizon according to on-board clock of ship, then you may see that the Earth has lived 1,000s of year in your 1 year absent. You would have actually traveled into the future using massive black hole as a time machine. Other effects will be same after entering the event horizon, just like the entering into smaller black hole. I think that's quite it for falling into a black hole. Certain death or access to other dimensions universe. Will the Earth ever fall into a black hole? Black holes are said to swallow planets, making them dead. Can the Earth ever get into one? The nearest black hole to the Earth is thought to be V4641 Sagittarii. Originally thought to be 1,600 light-years away from Earth, it's now thought to be 24,000 light-years away from Earth. This comes out to roughly 1.5 billion times the distance from the Earth to the Sun, or 22,300,000,000,000,000,000 miles. This is pretty far away. Black holes suck things in by gravitational force. The same force that keeps you on the ground is therefore the same force that keeps people from floating off the ground. So if you were to replace the Sun with a black hole with the exact same mass, the Earth would keep orbiting it as though nothing changed, although there would obviously be a fairly noticeable difference in how things operated on the planet itself. Panicking would likely be a bit of an issue, followed by everything dying. So let's say, for purposes of illustration, that V4641 Sagittarii has a mass equal to that of the Sun. The Sun has a mass of about 1.99 nonillion, that's a 1 followed by 30 zeros, kilograms. This causes the Earth to accelerate towards the Sun at a rate of 0.006 meters per second, not a typo. This is like going from 0 to 60 miles per hour in an hour and 15 minutes. This is just enough for us to always curve towards the Sun, but stay roughly the same distance away from it at all times. Our theoretical version of V4641 Sagittarii has the same mass but is much, much further away. If the Earth and the black hole were the only two objects in the universe, the Earth would accelerate towards the black hole at a rate of 0.00000000003 meters per second, 0 to 60 in only 309 trillion years. Keep in mind, the universe is only 15 billion years old. Also remember, there are other items in the galaxy that are much closer to us than 24,000 light-years. Alpha Centauri is the nearest star at 4.3 light-years, and we're accelerating towards it at a rate of about 0.00000000009 meters per second, so whatever gravitational effect our theoretical black hole has is going to be pretty much cancelled out by many, many other objects in the night sky. But what if the black hole were bigger? The largest black hole found has a mass 21 billion times that of the Sun. How does that change things? Well, our acceleration now comes out to 0.000000023 meters per second, 0 to 60 in 50,819 years. This is a stronger pull than Alpha Centauri's by a factor of about 260, but it's still going to be drowned out by various other objects in the night sky. You might have noticed that I haven't at any point stated how long it might take to get to this black hole. This is because the math gets complicated. Let's say you were to be kept in a fixed position a meter away from the singularity of that massive black hole. If you were to ask Isaac Newton how fast you would accelerate towards it once the fasteners were removed, he'd tell you that you'd be accelerating at 292,000,000,000,000,000,000,000,000,000,000,000,000,000,000 meters per second. However, this ignores the theory of relativity, which states that the fastest you can actually go is about 300 million meters per second, which is to say that there's no way you're accelerating, like that Newtonian figure would seem to imply. But let's briefly suppose you take away that universal speed limit and everything in the universe besides Earth and the black hole. The average acceleration between where we are now and a meter from where V4641 is now would be 13 billion meters per second, and the trip would take 2 days. Of course, by this same logic, the trip to Alpha Centauri would take 71 days. In short, you need to be really massive to move stuff around in space. Oh, and in case you were wondering, by the way, V4641 Sagittarii actually has a mass about 10 times that of the Sun. The Earth will be swallowed by the Sun in about 7.4 billion years. This pretty much means that the Earth will not be swallowed by V4641 Sagittarii, and that one was probably the best bet. Any way you slice it, if the Earth does fall into a black hole, you will have been dead for a very long time, so if anyone's trying to sell you black hole insurance, here's one reason, among many, why you might want to consider keeping your money. Alpha Centauri is actually a triple star system. Right now, let's deal with the biggest of 3 stars, Alpha Centauri A. If you fell into a black hole and looked back, would you see the end of the universe? Yes, you would. With some caveats. Did you know that watching stuff too fast can be dangerous for your health? Assuming the black hole is rotating, and most are, it's true that someone falling in will generally pass into the future of any event in the outside universe. When the last star in the galaxy winks out, billions of years after his journey, some of those final rays will reach our traveler. He can look back as he falls and watch history play out. For him, the whole thing will take barely a minute or two. But that ridiculously fast-forwarded view means that the arriving light is getting squashed into a short time span. That means its frequency will be way higher than normal, blue-shifted. The blue shift starts small, but grows more than exponentially as our friend watches. Pretty quickly, what started as visible light will become ultraviolet, and he indeed will see light that started as infrared. Soon after that, he will be watching the stuff we see with radio telescopes. Meanwhile, the formerly visible light will turn into X-rays, and then into gamma rays. Higher frequency means more energy per photon. The number of photons will also be going up crazily, as what was emitted over millennia is hitting the poor fellow in milliseconds. Yep, he will get completely vaporized. Just by having his view speeded up too much. The infinitely blue-shifted light also warps the spacetime into a singularity, besides for the one at the center of the black hole. This is, probably, a weak or gentle singularity, meaning an object can get to the final point without getting completely spaghettified by tidal forces. So just as our observer or his remains are watching the end of the universe, he also gets to directly experience a rupture in spacetime itself. Quantum gravity effects, unknown to humanity, will be manifest in all their glory. Too bad he only gets to experience this as a cloud of plasma. Now here's a more hopeful scenario. Suppose that the traveler is a celebrity back on Earth. His story gets passed down through the generations for a few centuries as mankind's abilities progress. Eventually, society decides to devote tremendous resources to a project that may save their hero. Using advanced future technology, they build a barrier surrounding the black hole so that no light or any other radiation can fall in. The barrier is perfectly effective and durable, and it lasts for trillions of years without itself falling into the black hole. Until all light has gone out from the universe. It might even need to last forever. The traveler sees the construction work quite soon after he falls past the horizon. He shouts, "Cut it out. You're blocking my view." But of course he can't send any message out of the black hole. Soon he is staring into the dark void inside the barrier. He may be annoyed, but the darkness is what's saving him from getting roasted. A few minutes later, all the infinite history of the universe has passed him by uneventfully. Yes, that's right, the space inside a spinning black hole will outlast eternity. As long as nothing happens to destroy it, like that super energetic zap of blue-shifted light. What will happen after that is beyond any physics that we currently have. Looking out toward where the universe used to be, our hero should now see a naked singularity, and we have no rules for what can come out of a singularity. Just to make things even weirder, the singularity is ring-shaped, and on the other side is a region where time loops around on itself. That just might indicate that our equations have lost contact with reality. But assume we ignore that and just take the simplest solution the math shows us. Then what happens is that a new universe begins, and the former black hole becomes a white hole, a black hole in reverse. You can fall out, but not go in. The traveler may survive his epic journey and get spit out to face the brave new world. Except that the new world will already have an infinitely long past history that occurred while he was still inside the white hole. Now I need to admit that I ignored one important point. Black holes don't naturally last forever. They evaporate by giving off Hawking radiation. So the future that can be seen from InSight isn't all the history of the outside universe, but only the first 10-60 years or so, till the whole finishes evaporating. That still is much, much longer than the time until all the stars die out, but it isn't anywhere near eternity. But the stuff about getting vaporized by blue-shifted light and the formation of a weak singularity still seem to apply to the best of our current knowledge. In the scenario with the barrier, we can make things even better. Let's say the inside of the barrier is perfectly reflective, so all the Hawking radiation bounces right back into the hole. That will prevent evaporation, so what I wrote before will still apply. The black hole and the person inside should literally continue to infinity and beyond. Is a black hole really a hole? No, black hole is not a hole, it is three-dimensional sphere. What you call a hole? When you fall in hole you will come out from other side, but this thing not happen with black hole. But you can call a wormhole a three-dimensional hole. Black hole is just like big sphere of very high mass, and the high mass is concentrated at its center, forming a singularity. A gravitational singularity or space-time singularity is a location in space-time where the gravitational field of a celestial body becomes infinite in a way that does not depend on the coordinate system. The quantities used to measure gravitational field strength are the scalar invariant curvatures of space-time, which includes a measure of the density of matter. Since such quantities become infinite within the singularity, the laws of normal space-time could not exist. And black hole is not like planet because planet don't have singularity at its center, and also black hole is formed when star dies. Let's see how black hole form. All star dies with supernova. When star runs out of hydrogen, it starts to fuse heavier elements, the core collapse. When this happens, a nuclear explosion occurs which is known as supernova. But the star's 3 or more times heavier than our sun. It goes through other process. If the remaining core is between 1.5 to 3 solar masses or sun mass, it contracts to form neutron star. If the remaining core is more than 3 solar mass, it contract to form black hole. The core is keep contracting beyond its event horizon and make the singularity at its center. Singularity means where a very huge amount of mass is concentrated. It forms stellar black hole. When black hole came in contact with other star, a dice of gas rotate around the black. If we discovered a rogue black hole approaching our solar system, could we evacuate to an exoplanet? And which would we go to? Breaking news. Scientists discover rogue black hole approaching the sun. Earth is in direct path. There's a couple scenarios here, and I'm going to play with every one of them. Earlier this morning, NASA released an official statement confirming the supposed approaching black hole. We have some time to prepare to see what we can do. In the meantime, NASA, SpaceX, the ESA, and other space agencies around the world are attempting to develop a plan to find some way to stay safe. Stay tuned for more details about our dangerous approacher after this break. Anderson Cooper has just blessed the whole world with this monstrosity of a CNN news broadcast. Since he's taking a commercial break right now, and you are sitting on the living room couch next to the nerd who already read the statement that NASA released and doesn't want to stay tuned, let's relay some information. Chances of the black hole being supermassive are extremely low. Generally, supermassive black holes are at the center of galaxies, and plus, if it were supermassive, then my answer would be short. There is no way we can get out of it. That's boring, though, so I'm not going to consider it. So, we've got a black hole coming towards our system. No matter what happens, in the end, we will not be orbiting our sun anymore. The variation in scenarios depends on where the black hole is going to pass through our solar system and how much time we have before it does. Earth could be torn apart, launched into the sun, launched into cold space, or fall directly into the black hole and then torn apart, obviously. Evacuating to an exoplanet is out of the question. The nearest exoplanet is multiple light-years away, orbiting Proxima Centauri, and we aren't even sure if it's habitable. In fact, it probably isn't. It would take us thousands of years to get there with our current technology. It would be far easier to create some sort of space colony and just avoid the black hole. Oh, looks like our commercial break is over. Scenario 1. Probable death by ice. It's a week after the horrifying news broadcast. The world can now see the ever-closer black hole's gravitational lensing against the stars behind it and a faint accretion disk whenever it captures an asteroid or two. Fortunately for most people, though, it's all going to be okay. The black hole isn't going to hit Earth. It's not the end of the world. Unfortunately for the people who know about physics, like NASA, armchair physicists, everything above that, and the government, we are going to be launched into empty space as a rogue planet. It's the end of the world. For the first few months, everything is fine. Woo. We survived. The black hole is going away. Then, winter comes. We freeze up. It starts to get darker. Crops fail, people start to starve. Luckily, the widely ignored space agencies and government, in all the panic, have been moving things underground. Farms start, malls start, the rushed and mediocrely built subsurface living spaces can fit hundreds of thousands, if not millions of people across the nation. Small companies join in, and they all start digging. Effectively, all of humanity pitches in and makes a whole underground network. The people who haven't yet starved or frozen likely move to these cities. But it isn't enough. It's likely that energy sources convert to almost entirely geothermal or nuclear, but eventually, something will go wrong or they will run out of energy. After all, space is cold. Death by ice. Black hole. 1. Humanity. 0. Scenario 2. Death by tides. This one is pretty short. The tidal stress on the Earth is too much. For a few days, earthquakes become extremely frequent, killing people by the millions. The black hole draws closer yet. People freak out and try to fix things, but really, there's nothing that can be done. Violent earthquakes eventually result in magma being drawn to the surface, initially beneath oceans, and then in massive volcanic eruptions, and finally, throughout the whole planet. Humanity is completely devastated and probably now extinct. If they aren't yet, then soon, the atmosphere is completely ripped away, the Earth is shredded to boulders and rocks, and every bit of matter existing on the planet is spaghettified as it is swallowed into the black hole. Black hole. 2. Humanity. 0. Scenario 3. We've got plenty of time. Time for the showdown. Humans have a chance now. We've got 100 years until the black hole gets here. Since the world isn't totally freaking out because the end of the world isn't tomorrow, NASA gets to work immediately. Since we can't get to another planet, all we really have to do is to avoid the black hole. Unfortunately, that likely means that we would have to undergo a feat many have said is impossible. We would have to get everyone off Earth. Everybody out. There's many ways to do this, but the most effective is by the use of a space elevator. This concept has been floating around for ages, but we have never tried it before, probably because we can't find a rope strong enough to do it with. But let's say we figured it out. Everyone gets excited. We've got a chance. Things are great. We start building space stations. All of our money and efforts go towards space because we have to save humanity and stuff. There's probably some treaty that all the countries signed to not get mad at each other until the humans are safe. That's weird for humans, but I think they can manage. It's been about 80 years. The lensing of the black hole is now visible through a backyard telescope or a pair of binoculars. People around the world are rushing to these new space elevators with some cheap brand name and watching the world fall below them as they rise further and further in the atmosphere. They can't help but think that their children would live a life without the planet they had always known. The trip up the line takes many hours, but when the destination is finally reached, the passengers have a view of Earth that they've never seen before. They are escorted to their quarters. Of course, this is only one of the hundreds of stations built, and only a portion of humanity will be saved. But maybe tonight isn't a night to fall into the whole sci-fi novel accompanying that idea. The time has come. Earth is either slingshotted or torn apart. Supposing nothing had gone wrong, humanity gets to watch it happen. Asteroid mining businesses boom. Suddenly, technology advances tremendously, and the new space age comes forth. It's a sad ending. Earth is destroyed. People died. Humanity lost its home planet. So, don't you think it's time to go find more? Black hole. 2. Humanity. To be determined. Thank you for watching. Please don't forget to like, share, subscribe the video.